Greetings, everyone. Today I'm going to go over nuclear chemistry. So up to this point, everything you've been taught within the realm of chemistry has been involving electrons, essentially sharing or having a surplus or deficiency of electrons to have some kind of interaction. Today we're going to look at particular particles that are going to be within the nucleus, hence nuclear chemistry. So reactivity standpoint and where those particular particles are, retained or sponged up or emitted. So nuclear chemistry involves the nuclei particles, so positrons, protons, neutrons, etc. So, if you can really count on your fingers or your toes, whatever, you should be able to do some of the arithmetic that you're going to see in this chapter pretty easily, at least the majority of it. Okay, so let's think of two routes for nuclear reactions. The first being the radioactive decay. So, in other words, things breaking down over time. Byproducts including radiation itself, so gamma rays or what have you. And then the other is nuclear bombardment reaction, so you can think of two nuclei colliding into one another in an inelastic form. So in other words, if you think of Newton's law of momentum, where things are elastic, things bounce off, and that momentum translates for each particle. Well, in this case, sometimes it actually things kind of come together and group off. Sometimes things break apart. It just depends on what kind of nuclei collide with one another. Okay, so let's get started with a little bit of historic context here before we begin. So the radioactive discoveries were noticed by Becquerel and the Curies. The Curies are a married couple. They shared the Nobel Prize in 1903 for the discovery. This was finding particular particles in photographic development, etc. Now, I'm not really going to go deep into it because I don't know the full story, but three types or split by both electric and magnetic stimuli. So we can think of the three different types of rays formed. So the alpha, beta, and gamma rays, the first being alpha, so those rays are bend toward a negative plate. So just like you can think of what you saw in the experiments early on in the text, maybe in chapter 2 or 3, I don't recall offhand. But then there are also the beta rays, which are opposite, so they're going to be deflected by the the negative plate. So presumably those will be negatively charged. And then the gamma rays, which are really influenced by neither. So it's really more of a form of energy of electromagnetic radiation. Okay, so there's going to be high energy electromagnetic radiation. Okay, so let's get into the nuts and bolts of nuclear equations here. Similar in balance to chemical equations, instead of bulk nuclei, you're really looking at one nuclide breaking down to form another. So for this particular example here, we have 226 over 88. So when that breaks off and alpha decay or alpha particle emission ensues, you're missing 2 electrons from 88 to get to 86. Okay, so and then above, notice how it goes from 226 to 222. That means you're missing 4 atomic mass units. So in other words, that's gone to helium. Again, that's going to be 2 plus. Right, so this is just going to be the nucleus. It's not going to actually be those a full helium atom itself. Okay. So see what you can do about balancing this particular equation here. Notice how I'm starting with bismuth. So at the bottom, you're going to want to put the count of protons because that's really going to give you the identity of that particular element. Okay, and then so you're going to be subtracting X number to go from 210 to 206. Notice how, again, an alpha particle is formed. You can just put this positive charge right there, 2 plus. Okay, so balance those nuclides out real quick and give me the identity or the atomic symbol for that particular species. So pause for 3 minutes. Alrighty, so we're going from bismuth, which is going to have an atomic number, or Z, of 83. So to lose 2 protons from alpha emission, we're going to get 81 as a count. So that's going to be thallium. Okay, so going from 210 to 206, we've lost 4 atomic mass units to go down to 206. Okay, so now let's go over some definitions. So positrons are going to be elements that actually have some kind of positive charge, so positively charged. So from the posi, particles, but mass contribution of an electron. So instead of, sorry, of an electron. So in other words, that's going to be simply a small negligible amount of mass contributed, like an electron would be, right? It's going to be a few orders of magnitude too low to be significant, as it were. Okay, so let's now look at a gamma photon. So a gamma photon is a particle of electromagnetic radiation of short length, or what? High energy. Remember, the shorter the wavelength, the higher the energy of that particular particle. Okay, so this is way down below that of, let's say, the wavelength of X-rays. Okay, how about nuclear force? So nuclear force is an attractive force. You can almost think of it like the glue, the nucleus. So it keeps nucleons So nucleons just broadly are just any type of nuclear particle bunched together. So just generally protons, neutrons. Within short distances of one another. So the next is the shell model of the nucleus. So some almost can be thought of the same way you think of the Aufbau principle for electrons, though this is just referring to nuclear particles or nucleons. So in other words, it's almost like a babushka doll. It just kind of builds out and expands more and more and more as you have more particles within that nucleus. And of course, everything that's going to keep it grounded are going to be those electrons that are orbiting about it. Okay. So the magic number, this is in quotation marks, is a completed shell. Of protons and neutrons. So I'll just put in shorthand Z and N, whereby that cluster is stable. So depending on that count of Z and N, that may dictate how stable that particular isotope or element is and how flimsy it could be in terms of emitting particles and the like. Okay, so one thing to take a look at in your text is the band of stability. You can find that on page 21.4. Page 977, figure 21.4, page 977. A linear relationship between atomic number Z, that would be the x-axis, so, going horizontal. And then the neutron count, which is going to be the y. Okay, so you'll see sort of like a perfectly, up until Z equals 20, and Z equals 20 is calcium. So this is the Z count. This is the N count. So it's perfectly linear. Again, going at a 45-degree angle from the origin. And then at about 20, that's when things start to kind of veer off. And you have a higher band of stability, or you have a higher probability of stability where the N count is going to be higher than the Z count. So you notice that as you get further up, or you get higher an atomic number on the periodic table, and you'll notice that some of those average atomic masses are going to be slightly higher, right? So it's not going to fall right in line and lockstep. 25 plus 25 is going to give you exactly 50. Like for instance, for manganese, manganese is an average about 54, 55-ish. Okay, and then manganese atomic number is actually 25. So in other words, there's an additional 5 atomic mass units there that are going to be averaged out. So again, something that you can actually quantify and keep, without it decaying and breaking down over, a reasonable period of time, and that's going to be a stable isotope, so to speak. Okay, so let's think of the different types of radioactive decay. I've already referred to alpha emission. Again, that's just something giving off this particular particle. Seen that with lead, like a lead block, for instance, with some of the experiments in chapter 2. Then beta emission, so this is resulting in a high-speed electron from an unstable nucleus basically coming off. So in other words, you can think of maybe a neutron splitting that off, and then that negative charge goes away, and then there's a positive charge as a result that's resting there. Positron emission, where an unstable nucleus emits a positron. Again, this is going to be beta plus. Beta emission should be beta minus. Okay. Sometimes you'll also see it like this. So P 1 and 0. So this is going to represent a nuclide. It's not going to represent phosphorus. It's a little lowercase p. Okay, so that 0 right there at the bottom is actually going to represent no charge itself, or sorry, no positive charge, even though, sorry, I've got this backwards. There should be 1 here and then 0 for the actual weight contribution. Let me redo this. Okay, so 1's going to be on the bottom. Again, that's going to represent the charge, but this is going to represent that there's going to be 0 contribution of mass. Okay, so mass on the top, positive charge on the bottom. All right, number 4, electron capture, or the decay of an unstable nucleus by capturing an electron from an inner orbital of an atom. So essentially you're just sponging up electrons from some kind of lower energy or inner orbital electron from that atom. Okay, so some of the you wouldn't say that was a valence electron. You'd say something kind of buried in underneath that's going to be lower in energy. Okay, so gamma emission is an excited nucleus that is unstable, which emits a gamma photon to return to a lower energy state. In your text, you'll see the gamma photon is represented, by some kind of sort of bang, if you will. Sort of like a firecracker going off, I guess. Spontaneous fission, so that's going to involve a heavy, unstable nucleus greater than 89 that breaks apart into lighter nuclei and energy is released. So this is sort of where nuclear reactors basically harness electrical energy or energy that gets stored and goes into the energy grid. Okay, so you can look at figure 21.2 on page 973. Without looking at the description, what kind of decay arises when a diagonal motion occurs? So in this particular instance, we're going from 238 to 234 in terms of atomic mass units, and then 92 to 90 from the charge. So uranium going down to TH, which stands for, sorry, my memory isn't the best right now, thorium. Thor. Okay, so what kind of decay is that? That's going to be alpha decay. So just alpha sign like that. Okay. Now, what kind of decay arises when a horizontal motion occurs going z equals 90 to z equals 91? So that would be beta decay. Okay. So again, the charge is going from plus 90 to plus 91 within that nucleus. So in other words, it's basically emitting some kind of electron from its neutron source or something like that. Okay. And therefore, that actually changes the identity of that particular element. Okay, moving on, let's talk about transmutation. So that's changing one element to another. Surprise, surprise. With nuclear bombardment, with nuclear particles like alpha particles ejecting photons in the process. So you can almost think of this like hitting, you know, some billiard balls, and some of them kind of sticking close together and others kind of diverging off from that cue ball, smacking into it, right? So try to balance some of these nuclides and see what you come up with for your answers, what's in the blank here. If you want to take a look at the text that's on problem 2156 on page 1010 and 21.55 on page 1010 as well. So there's something that's going to be absorbing a helium nuclide or nucleus rather, and then you're going to form 13 atomic mass unit N, and then some neutron. So notice that the neutron is not charged, but it has an atomic mass unit of 1. Okay, so take a few minutes and pause and see what you come up. Okie dokie. So going from PO to lead, that's going to be 210 to 206. So you're dropping 4 atomic mass units, 4 at the top. Notice how you're just sliding to the left 2 spaces on period 6. So going from 84 to 82 for your Z value. So in other words, you'd have to lose 2 protons, which would go right there where helium is. Okay. Now, H3 or tritium is a more rare form of hydrogen. But if it loses, let's say, a beta particle, then it's going to increase in charge by 1, right? So in other words, I would just write this beta. Notice how I have sort of a like elongated staff there at the bottom. So that's going to be different than, say, boron, like how I put in example C. So notice how I also put a negative sign here at the bottom. That's going to be negatively charged. So in other words, it's going to be an electron, okay, or electron emission. Okay, so problem 21.55, page 1010. So we have something with helium, which is again a alpha particle rather, to yield 13 nitrogen and 1 neutron. So just doing the algebra here, so we have 7 on this side, 2 on this side, so we need 5 to account for all of the charges. And then above, so we have 14 on the right, so we're missing 10, so we put 10 over there. And again, the species that you would choose from this is going to be dictated by this number at the bottom here. Okay. All right, so let's take a look at the rate of radioactive decay. So this is going to be the same type of thing you'll see from a half-life or first order reaction from your kinetics. So in other words, there's the decay of a particular starting material, or in other words, a count of nuclei. So it's pretty much going to involve the same math from chapter 13. You're going to use the integrated rate law first order. So if we were to do that, let me pull that up real quick. Okay, I'll pull this up for you. So this is on page 1009, problem 21.37. So this is C137 cesium decay from Fukushima. Okay, so let's move this over and look at the screen. Sorry about this wonderful production I have going here. Okay, so the screen's focused here. All right, so the half-life is given to us, and that's 30.2 years. So that's the amount of time it takes for things to break down, which, in other words, to see this drop down to about a quarter of what it was being spewed out and leaked elsewhere, pretty much in our lifetime, we'll see it maybe go down to a quarter of what it once started out with. So the first order half-life is going to be equal to T1 half. Again, that represents the half-life. And then, instead of just doing the natural logarithm of 0.5 or half, right, that's just going to give you 0.693. And that's also going to be negated. Remember that natural logarithm, if you have something that's less than 1, it's going to be in the negative. So essentially you would just divide this particular number by k, to give you your half-life. So in other words, we have the half-life already. What we're really looking to solve for here is k. So just rearranging the algebra, substituting these two, the denominator and what we're to solve for. K is going to be equal to 0.693 divided by 30.2 years. So our rate constant is going to be 2.29 times 10 to the minus 2 years inverse. So not too fast. Okay, and now we're looking at, this is the first order integrated rate law. So now we have negative kt. We're really going to be solving for t. We have k already. And the question asks when we will get down to about 5% of what we started out with back in 2011 when the spill occurred. So, so we're going from n at a particular time, which is assumed to be 5%, or at least that's the target we're looking at. And then, this is going to be 100. So that's where you see the 0.5 coming from, or 0.05 rather. So if you take the natural logarithm of 0.05, you're going to get negative 3. Both of these negative pieces cancel out. So in other words, you're always going to be left with a positive value, right? Because we're not going to go back in time. Okay, so t is going to be, or that time is going to be equal to 3 divided by k. Okay, so what we originally solved for here up above. Yeah, right there. Okay, so 3.00 divided by 2.29 times 10 to the minus 2 years inverse is going to give you roughly 131 years. So in other words, by the time we get up to 10%, or down to 10% rather, we'll probably all be pushing up daisies. Okay, so if you thought that particular math was long-winded, boy, are you in for a treat with this one. Okay, so calculating the energy changes in radioactive decay, so this is really sort of minute detail here, is what is referred to as a mass defect. So it's used to actually calculate the binding energy. Okay, so per Einstein's equation here, so your binding energy, or capital B, capital E, is equal to change in mass, and then the speed of light squared. So in other words, what the change in mass is going to be is really going to dictate what the binding energy is going to be. So if you go over to page 1010, problem 21.48, take take a look at that problem and see what you come up with. Now, if we're talking about fluorine and, it's going to undergo some kind of decay, fluorine is going to have 9 protons, 9 neutrons, and 9 electrons. So it's within that linear portion of the band of stability. Okay, so now do some math, look at the actual values, the exact values. I think there's up to 7 or 8. 7 or 8, nope, actually 5 decimal places to report. Okay, so for every neutron, it's going to be 1.67262 times 10 to the minus 27 kilograms. Proton, it's going to be 1.67493 times 10 to the minus 27 kilograms. And then electrons are going to be 9.01938 times 10 to the minus 31 kilograms. So, with each count, again, it's going to be 9 of those each. So sum all those up and see what kind of difference you get with respect to an actual atom of fluorine, which is going to be, let's see here, 2.98915 times 10 to the minus 26 kilograms. So see what kind of difference you come up with and figure out what the binding energy is from that. Delta M is equal to, binding energy is equal to delta M times the square root or square value of 3.00 times 10 to the 8 meters per second. Okay, so pause for about 10 minutes. It'll take a little while for you to crunch all that. Okay, so here are all the particles lined up. So I have neutron, proton, electron, so 9 counts of each. So 9 times each one of those individual mass contributions. And then on the right, they're all those products are going to be summed up together. And you're going to subtract this particular value from, again, 18 fluorine. So in total, that delta M is going to be 2.445 times 10 to the minus 28 kilograms. Sorry, kilograms is kind of cropped out there. All right, so that's the delta M. Bunch of grunt work calculations there. I'm glad I had this before. So binding energy is equal to the change in M, or delta M is equal times C squared. So plugging that in and multiplying it by 2.998 or 3.00, whatever you want to call it, times 10 to the 8 meters per second, squaring the whole thing, right? So it's going to be meter squared second squared times kilogram, or meter squared over second squared times kilogram, which is going to represent joules, right? Those are the base units of joules, okay? And essentially, you're going to have 2.198 times 10 to the minus 11 joules for every particular element of fluorine that has that particular mass defect. Okay, so it's probably one of the longest-winded problems you're going to deal with, at least with lecture for this course, since we're going to be getting into organic chemistry, which is completely jumping ship from this. Okay, nuclear fission is when a subatomic particle slash atomic nucleus collide at high energy, the speed, and fuse together. So lighter nuclei are yielded along with energy. Again, that particular energy gets harnessed and used. Okay, so when a particle of matter and antimatter collide or fuse, a gamma ray is produced. Okay. Neutron capture is when nuclei absorb neutrons. So in this particular instance, we have 56 iron, which is going to sponge up 3 neutrons. Again, 0 charge contribution, but 1 mass atomic mass contribution apiece. So that's going to bump you up from 56 to 59. And again, that Z count is going to be unchanged. Okay, so that's the intermediate. And so that would suggest that this is slightly unstable. So as a result, you're going to generate cobalt. So cobalt, if we were to look at a periodic table, cobalt is going to be right there, which is 1 up from iron. So it's going to be 27, and that would make sense because we've lost 1 charge. Okay, so is anything changing with the atomic mass? No. Okay, so that's what is an example of neutron capture there. Okay, so in other words, this is really sort of an intermediate, to make a sort of a bracket. Not to suggest that's some kind of concentration or anything. It's just some kind of intermediate. Okay, so see what kind of starting material or starting element you would have given what's in 21.56D. Again, on page 1010. There's a little bit of a typo here, so I've corrected it. Same blank spot, but the count of Z is going to be 26. So, just to do some simple math here, you're really not adding anything to charge from a neutron. Only thing you're really doing is adding to the atomic mass unit count. So in other words, it should be 58 iron, right? And that identity does not change. Sorry about the blur there. Okay, so after all this, how is radioactivity actually measured? Well, with a Geiger counter. So measuring decay events per unit time. So it's, in other words, a becquerel is essentially just 1 decay event per second. So in other words, it's decay rate. Okay, so Geiger counters are typically used in areas where there's high radioactivity, and they can kind of monitor it. So for the next 3 historic examples that I'm not going to go into gory detail about because we have enough to keep us up at night. These are just some kind of measure counters to just see how much radioactivity is in a particular environment. Okay. So some historical events with nuclear energy. So about a year before I was born, this happened at 3 Mile Island. This is in Pennsylvania, just across the river from Harrisburg, which is actually a pretty nice city. And if you ever get around to checking out the Capitol, it's really something. Something you can look at on, via Wikipedia. There's plenty of information on this. Thankfully, the residents weren't tremendously affected by this, tremendously in a bad way. That's good. They've done some case studies to see if they had any greater, case studies of, cancer rates and things like that, and it's been relatively unchanged. Central to eastern Pennsylvania is kind of a hotbed for nuclear waste and that kind of thing, and so places like Philadelphia and stuff like that, they tend to have a lot of nuclear waste buildup. Okay, so Chernobyl is one of the more well-known, although this happened in the mid to late 80s. I believe in 1986 or 87, but don't quote me on that. So they have had to have whole buildings basically encapsulate these areas, building sort of like warehouses around some of these reactors and sites where things kind of went awry. And also, from what I've been reading on the news, there have been some wildfires surrounding the area, so it's kicking up some nuclear waste that way, which is not good. And then finally, Fukushima, which is the most recent. So this happened roughly 9 years ago, a little over 9 years ago, I guess. And this happened, beyond the aftermath of a tsunami and basically killing their cooling system. And it was a big old mess that they're looking to monitor for a very long time. So at any rate, bear in mind that nuclear disasters like this don't happen often. Again, these are probably broken up. This is probably broken up by a magnitude of roughly 24 years, 25 years, something like that. This is about 8 between these. So the occurrence of it happening isn't regular. Could we find a more ideal solution? Maybe, but it is what it is. There's plenty of nuclear power that we use in the States here. There's plenty of power that gets used in places where you think there's a lot more progressive methods or ideas. Like, for instance, France is definitely heavy-handed on their nuclear power usage, et cetera, et cetera. So I'm not going to go on any type of, tirade or crusade or whatever you want to call it about this. It's just something that you might want to know and you can read about on your own time. All right, so to wrap things up, again, what I just spoke about with the some of the disasters that occurred, as well as some of the things that I'm going to go over with you here. These aren't really, these are really more for application purposes. This isn't something I'm necessarily going to test you upon. Just something that you might want to look into if you're getting into medicine or looking to get into medicine. Maybe, you're already at a facility that uses some of these techniques. So this is just really for awareness, etc. So some medical applications and measurements here. First off, let's go with some measurements. So radiation is absorbed in tissues or cells, right? So for some therapeutic effect. This is going to be measured in grays, so everything's proportional, right? So joules of energy absorbed per kilogram of body mass, right? So you also have gamma radiation, so those are higher energy rays than X-rays, like I said before. So looking to kill a cluster of cells that's kind of gone rogue and proliferated out of control. Now there are some radionuclides that are used in table 21.7 on page 1002. You can see some of their therapeutic applications. Some involve thyroid cancer, some involve other types of cancers like prostate, etc. Okay, so again, I'm not going to quiz you or evaluate you based on your memorization of all this. This is just for your own information. Okay. Now, relative biological effectiveness, or RBE, is simply a measurement of sieverts. Always mess that up. So that's going to be in meters squared, second squared. Notice how the kilograms is gone. So this is really more of a measurement, the same way you would think of a therapeutic index. So in other words, how much benefit, it's sort of a weight of how much benefit to, detriment that particular therapy imposes, right? So ideally you want things to be better than worse, right? So if you're, destroying cells or causing other type of cancers or whatever, when you're trying to get rid of one, it's kind of more of a game of whack-a-mole and more deadly than it is effective. So this is something that that scientists and doctors look to measure and monitor. Okay, so the last thing to look at, and literally is imaging, means of imaging, is positron emission tomography, or PET. So powerful tool in medical imaging. So via glucose metabolism, that's just the best way that they can image brain activity, let's say, for instance, or some kind of metabolic activity or breaking down of glucose itself. So administering low-weight nuclides in place of C12 and 16O with, let's say, low-weight carbon or low-weight fluorine. Okay, so, it's not something that you're going to administer time and again and again and again. This is something that you're going to look at, maybe once to see if there's any type of brain atrophy or what have you in someone's head, for instance. So this is something that's very powerful in terms of imaging and assessing what's going on. So some people that have CTE, or I forgot what the actual acronym is for, some kind of brain damage, some sports players, say, or let's say mixed martial artists or boxers, they all have some kind of degradation over the years of just getting hit so many times. I mean, it's unavoidable now, right? It's kind of a fact that over time people, that's the cost of traumatizing your brain, essentially, whether it's intentional or not. So at any rate, hate to leave things off the way they are here, but this is still important research that goes on, and it's given us better insight into therapies and things of that nature. So hope you enjoyed it, and I will see you next time. Thanks so much.